Hey everyone. So today I wanted to talk a little bit about the central limit theorem and do a little bit of a demo. But before I do that, I want to make sure that we have these two notions of population and sample and corresponding notations all absolutely clear. So remember that the population is like the whole world, or all the people in Michigan, or all the phones manufactured at a given factory. Now, if those are the things that we're interested in studying, they are too big, right? We can't ask everyone in the whole world a question. We can't measure the shoe size of all the people in Michigan. There's just too many of them. So we can't ask everybody in the whole world, for example, what they think of the World Health Organization's handling of the coronavirus, but we could randomly select 1,000 people and ask them. And we can't measure the shoe size of everyone in Michigan, but we could randomly select 50 people and measure them. And we can't check every single phone that comes out of a factory forever to see if its battery life is what it says it is. It's just not feasible quality control measure, right? But we can take a sample of them, say a sample of even 10 or 15, and check their battery life. And in each of these cases, we're measuring something and then going to compute something, right? Like we're measuring approve or disapprove for people being asked about the WHO, or measuring the actual size of people's feet in the second case, and measuring how long the battery lasts on 15 phones. So the first one is an example of where we're looking at the proportion of a population, right? Like a poll where we're asking you approve or disapprove, and then the natural thing to report would be the proportion of people who approve or disapprove of the WHO's handling of coronavirus. And in that case, right, when we're talking about proportions, we would use the symbol P bar to be equal to the proportion of people who say approve of the WHO's handling of coronavirus. So that's gonna be a percentage. And to compute it, we divide the number of people approving by the number of people asked. So that would be the number of people in the sample. Now, this theoretical figure that we don't know and can't know, the true proportion of the population that approves of the WHO's handling of coronavirus, we use the notation just plain old P. For means, which is the natural thing that we would measure for the other two cases, right? The average shoe size, or the average amount of time in the battery life of these phones, the natural thing to measure would be the mean. And so if we take one of these samples and compute the mean, right, we know that that's just the average. And there is a true mean, right? But it's, as we said, it's not something we can know. And the convention in statistics is to use the lowercase Greek letter mu to represent that. And in each of these cases, there's a standard deviation that we can compute. And in the case of the population, the convention is to use the lowercase Greek letter sigma, and the standard deviation that's computed in the usual way for the sample is just S. Okay, so with those things down, let's take a look at how these sample values behave in sort of a grander scale. Okay, so here we have one of these little simulations from our textbook, and what I want to do is just walk through it with a couple examples. So here's the idea. This graph is representing the actual distribution of values for some statistic that we might measure in the population, right? So that's why these Greek letters are appearing over here, mu and sigma. They are the population parameters, right? The average value of this, whatever we're measuring, shoe size or something, is 16 for this population. And then there's a population standard deviation that tells us about, like, 68% of the population has a shoe size between 10 and 20. And when we can interpret this as a probability distribution by saying, okay, well, if I randomly pick one person out of this population, what's their shoe size going to be? Well, we can do that by saying, okay, let's select a sample of size 1 and measure the shoe size, right? So we randomly selected a person and their shoe size happened to be 11. And I can do this again and again and again and again and again. And most of the time you'll see we'll get values that are sort of in the middle. But, you know, one person is not enough to be representative of this entire population. If I want to know what the average shoe size is of this population, measuring one person's foot is not going to give me an accurate value, right? So what I'd want to do is take a whole bunch of people, say 25 people, and measure their feet, right? So now if I take a sample of 25 people, and I can take one sample of size 25, and there's the distribution of those 25 people. The average is 16.64, so that's pretty close, right? And the larger the sample, the more accurate a mean I'll get. So this one is sample size 50. The average is 15.62. So an important thing to notice is if I take a different sample, right? If I do this again, I'm going to get a different sample of people, and I'll get a different mean. Now the mean I got is 16.38. And if I do it again, I'll get another different mean. So you're watching this number over here, the X bar number. Every time I randomly select 50 people and compute the mean, I'm going to get a different value. And some are going to be more accurate than others. Like that 16.04, like this 16.04 is super accurate, but 15.56 is much further away from the true mean of 16. And the bigger the sample size is, the less likely that is to happen, right? Okay, so let's go back to a smaller sample size for a minute and look down here at this chart. So remember that our shoe sizes are normally distributed. So you take a random person, 68% of the time they're going to have a shoe size between 10 and 20, and 95% of the time they're going to have a shoe size between 5 and 25, and 99.7% of the time they'll have a shoe size between 0 and 30. Or, you know, it doesn't have to be shoe size, this value of this variable that we're measuring. So now down here, what we're going to do is keep track of the sample mean. So let's go back to just picking one person at a time and measuring their shoe size. I get that single person had a shoe size of 18. So the average of this sample of size 1 was 18. And so down here, I'm going to plot the sample mean that I'm getting, right? So I've got one sample, the mean is 18. And now if I do this again, now I happen to pick somebody that has size 20. And so the sample mean of that sample of size 1 is equal to 20. And the statistic that's been being computed down here is actually the average of the means from those samples. So this is the average of two averages. And I can keep doing this. And if I do it for long enough, let me do 100 at a time. I don't know how many it'll let me do. So now I've got 520 different samples having been taken. These are samples of size 1. And the distribution is looking very much like the distribution up here. And that's not a surprise because we're taking samples of size 1. It's like we're studying the entire population. So now let's up our game. Let's do something less silly than just measuring one person to try to guess the average of this random variable for an entire population. Let's at least look at 10 people and make this measurement. So now if I take a sample of 10 people and measure them, so here's the distribution of the actual data. The average from this data was 16.8. So I'm going to count, I have now that average of those 10 people I now have as 16.8. So I've got one sample mean that was 16.8. So that's what this bar is. If I do it again, I'm going to get a different value. This time I got 15.9. So now I have two sample means. One was 16.8 and one was 15.9. The average of those two is 16.35. And now I can keep taking these samples, again, samples of size 10. So now I pick 10 more people and I get another mean and another average of means. I do it again, and I can do it again, and I do it again and again and again and again and again. And you'll see, compare this to the last one where we had things kind of going all over the place. This is a really tight grouping around the true population mean of 16. And now let's do 100 of these. Okay, so now I have 310, right? 310 different samples of 10 people. So pick 10 people, compute the mean. Pick 10 people, compute the mean. Pick 10 people, compute the mean. Do that 310 times, and then take the average of all those means. That's what this value is. But this distribution of sample means, what that's showing us is that if we use a sample of 10 people instead of a sample of 1, then we're going to, our spread is going to be much lower, right? Instead of being spread out that in a way that matched the original distribution, it's now, instead of having a standard deviation of 4.45, this has got a standard deviation of 1.42. And the way we interpret this is that 68% of the time, when we sample 10 people and compute the mean, that mean will be in this tighter range around the true mean. Okay, so now let's go up to a sample of size 100. All right, so we're going to take a sample of size 100, and that's the distribution of the data from that one study of select 100 people, compute the mean. The mean was 15.86. So now we've got one sample mean that's 15.86. And now, just to see the central limit theorem in action, we're going to do this study again. Pick another 100 people, do the same thing. Pick another 100 people, do the same thing. Pick another 100 people, pick another 100 people, pick another 100 people, and so on. I'll do 100 samples now. Each one of those is a sample of 100 people. Now look at how tight this distribution is. But do you see how small this standard deviation is? The standard deviation when we had a sample of size 10 was a little bit bigger than 1, and now this is less than a half, which is a lot smaller than the population standard deviation of 4.45. So that means that 68% of the time, right, we're going to get a sample mean that's within 0.45 of whatever the true mean sample mean is, and that is the true mean of the population. So the lesson here is that sample size matters. The other lesson that comes from the central limit theorem is that it doesn't matter what your original data looks like. So it's maybe not a huge surprise if we have a nice normally distributed population variable that we're getting things that look like a normal distribution over here. But it doesn't matter what we pick. The uniform distribution, we can do the same thing. Let's take 100 samples. You see what this looks like? It looks like a very skinny bell curve. If we use even something kind of wacky, like a partially skewed, the population mean in this case was 7.38 and the standard deviation was 4.27. Now down here, we have a mean of means of 7.35, very close to 7.38. And a standard deviation of this distribution of sample means is, again, about a half. So that's partially skewed data, even bimodal data, right? So that means there are two kind of peaks of most frequently occurring values. We're still going to get a much tighter grouping by using a larger sample size. Like compare that to if we do a sample of size 10. Right? This is, it's starting to look normal, but it's still very wide. And if we use a sample of size 5, right, then it's even messier. What we want is one of those nice, tight, narrow, bell-shaped curves. And the central limit theorem says that we'll get one. If we have a big enough sample size, it doesn't even matter what the original distribution is. Okay, so that is a little bit of a walkthrough about this whole process. Hopefully it helps you with some intuition, right? The key thing is the largest random sample that's feasible is what you want to use for your study.